In this video, we'll look at the properties of reciprocal, also known as secondary, trig functions. So normally I do the work as I go, but I'm going to read to you here if you can't read my writing. And I'm going to show you some stuff on the graphing calculator. Okay, first things first. Where the primary trig function has a 0, I'm over here, that's where the secondary trig function has a vertical asymptote, and vice versa. Wherever the secondary trig function has its vertical asymptote, the primary will have a 0. Second, wherever the primary function, and for primary, just in case you don't know what I mean yet, I mean like sine, cosine, or tangent. Wherever a primary function like sine is above the x-axis, so is its secondary function cosecant. Same goes for below the x-axis. Wherever cosine is below the x-axis, so will secant be below the x-axis. Third one, they have opposite increase and decrease. Wherever the primary trig function, like tan, say, increases, the secondary function cotangent will be decreasing, and vice versa. Wherever the primary function, say sine, is decreasing, cosecant will be increasing. They also have opposite local maxes and local mins. Wherever there's a local max on a primary function, that'll be the local min of its secondary function, and vice versa. Wherever there's a local min on a primary function, that'll be a local max of the secondary function. And finally, number 5, the primary function and their secondary functions have the same period. So sine has the same period as cosecant, and cosine has the same period as secant, and tan has the same period as cotangent. But let's take a look at that. So for example, cosecant. So I'm going to make a graph first of sine. So y equals, let's graph sine of x, close the bracket. And let's also graph, there's no cosecant button, so we'll just type it in straight up, y equals sine 1 over the sine of x. That's your reciprocal of sine, or cosecant. Let's look at what they look like. The graph of sine is in blue, and the graph of cosecant's in red. So take a look. First of all, can you see wherever sine has its zeros, that's become a vertical asymptote? Here, I'll use a pencil to point. There's a 0, a vertical asymptote. A 0, a vertical asymptote. The blue sine 0, a vertical asymptote for the red cosecant. Number 2, wherever it's above the x-axis, check out where blue's above the x-axis, so is red. Where blue's below the red axis, so is red. Number 3, they have opposite increase or decrease. When the blue's going up, the red's coming down. And when the blue's going down, the red's going up. Number 4, local maxes become local mins, and vice versa. This blue's local max is this red's local min, whereas this red's local max is the blue local min. And finally, they have the same period. That is, if you look at a sine wave, the scale's not quite clear on here, but the period of sine wave, I hope you know, is 360 degrees, or 2 pi in radians. So does cosecant have a repeating pattern that takes place over 360 degrees, or 2 pi. I'm going to write that in here. I think that's worth noting. The period is 360 degrees, also known as 2 pi radians. You can see the domain. The domain is x is an element of R. I'm talking about cosecant now, the red one. You can see its domain is all real numbers except where their asymptotes occur. Where does the asymptotes occur? Oh, screensaver went on there. The asymptotes occur at multiples of pi, so that's in radians. So for example, at 0 and pi and 2 pi, 3 pi, 4 pi, but also negative pi, negative 2 pi, there's an asymptote. That's how this domain is generated. It's n, any integer, times pi. So negative 3, negative 2, negative 1, 2, 3, 4, and 0 pi, all are where the asymptotes occur. The range of this cosecant, the red again, is the set of y's, an element of R, such that the y's are either greater than or equal to 1, that's all these positive parts, or y is less than or equal to negative 1, that's all these negative parts. Notice these U-like shapes, I should probably pluralize that. But with asymptotes, they're not parabolas. They maybe look like it, but these are all asymptotes, as I mentioned. So don't think of these as parabolas. Think of them as you like, but they all close in on these invisible vertical asymptotes. Notice also cosecant is an odd function. That is, if you rotate this 180 degrees about the origin, you'd get the same thing back. And as I already mentioned, the period is 360 degrees, or 2 pi radians. Let's switch it up a bit. Let's go with secant. So let's look at the graph of cosine compared to the graph of 1 over cosine. It's going to regraph it for us. That blue is going to be the cosine wave, and the red's going to be secant. Very similar shape, just as sine and cosine are quite intimately related. So are secant and cosecant. They're just 90 degree or pi over 2 shifts of each other. Let's check the properties quickly again. Notice wherever there was a 0 on the blue again, that became a vertical asymptote for the red. That is, the primary function zeros become vertical asymptotes for the secondary function. Notice wherever red is above the x-axis, that's where blue is above the x-axis, and where blue goes below the x-axis, that's where red's below the x-axis. Notice that when red's going down, blue's going up, and when blue's going down, red's going up. That's number 3. Notice that all the primary local maxes, like here, here, and here, are secondary local mins, and all the primary local mins are secondary local maxes. Oh, and one last one. The primary functions have the same period as their secondary functions, so I should write that in here. The period of secant is just like the period of cosine, which is 360 degrees, also known as 2 pi. So just some notes on the domain. Okay, this is probably one of the hardest things you're going to see in this unit, if not this course. The domain is the set of x is an element of R such that x cannot equal this formula, comma, and is an element of I. And notice all this formula does is generate the asymptotes. The asymptotes, it's hard to see on the scale here, the asymptotes occur at pi over 2, 3 pi over 2, 5 pi over 2, 7 pi over 2. That is pi over 2, but you can't just use n because then you'd get 1 pi over 2, 2 pi over 2, 3 pi over 2. We only want odd numbers, 1, 3, 5, 7, and -1, -3, -5, -7 pi over 2. Sub in different n's here, like 1. 2 times 1, take away 1. That's 1 pi over 2. Sub in 2 here. 2 times 2 is 4. Take away 1 is 3 pi over 2. Sub in 3 here. You get 3 times 2, take away 1. That's 5 pi over 2. See how it's generating what we need? Once a student of mine generated his own formula, you can actually get it just by rainbowing in this pi over 2 times 2n minus 1, and when you simplify, you get this formula. You can also look at these asymptotes as taking any n, any integer, timesing it by pi, and subtracting pi over 2. So go like 1 pi, take away pi over 2 is a half pi over 2. Or 2 pi, take away pi over 2 is 3 halves pi over 2. Or sub in 3, that's 3 pi, take away pi over 2 is 5 pi over 2. So either of these formulas will generate the domain. What's the range? Just like the last function, the set of y is an element of R, such that the y's, the screensaver, the y's have to be greater than or equal to 1, or less than or equal to -1. And again, with secant, we get this U-like shape, but with vertical asymptotes. And again, last time I mentioned their asymptotes, they're vertical asymptotes. Also notice here, unlike cosecant, secant is an even function. It reflects perfectly across that y-axis. If you flip it over, you get the exact same thing. And as I mentioned, its period is 360 degrees, or 2 pi. Remember too, a lot of people get confused. Cosecant is the inverse of sine, sorry, that's a bad word. Cosecant is the reciprocal of sine. Secant is the reciprocal of cosine. Very easy to get those mixed up. This one is the secondary for sine. This one is the secondary for cosine. Let's look at tangent. I'm going to change up my calculator to tan. And we'll take a look at that graph. So tan looks a lot different. It's graphing tan right now in blue. That's the tan x function. And then in red, we'll see cotangent. And that should hopefully be easy enough to read. Notice in a couple of the graphs, like it looks like it ends there. Please believe me that it doesn't. It goes on forever. It's just the technology's bugging out a bit here, but it's approaching that asymptote, never touching. It's going up for infinity. On all these pieces, they go up for infinity. Let's look again, comparing blue to red. The primary function zeros become an asymptote, and vice versa. Look, where this red function hits 0, that's an asymptote for blue. I'll say that again. Blue 0 becomes red asymptote, and red 0 becomes blue's asymptote. That's this number 1. Number 2, blue and red are both above the x-axis at the same x. And when one goes below the x-axis, so does the other. That's number 2. Number 3, they have opposite increases and decreases. When red's going down, blue's going up. And when blue's going up, red's going down. Number 4, wherever there's a local max, well, we don't have any here, so 4 doesn't really apply to tan or cotangent. And number 5, they share the same period. Notice that the period's different here. The period for tan and cotangent is 180 degrees, which is equal to pi. You know, I wish I'd written it like that over here. I don't like this. Brackets can be interpreted as times. I'm going to write this as equals 2 pi. I like that better. I think it's better communication. I'm going to change this one up here too, because I don't want it to be read as times 2 pi. 360 degrees is equal to 2 pi radians. Back to cotangent though. Its domain is, notice, the same as the domain of cosecant. The set of x is an element of R such that x can't be any multiple of pi. These red pieces of cotangent have an asymptote every pi. 1 pi, 2 pi, 3 pi, 4 pi, 5 pi, 6, and so on. Also negative. Same asymptotes as cosecant. But unlike cosecant, notice that cotangent goes up forever and goes down forever. That's why its range is unlimited. The set of y is just an element of R. Its shape could be best described as an inverted shape of tangent. It's the same as the blue, but inverted, going the opposite direction. And it's hard to see with these blue lines at the same time. I think I might clear those. But check out that red graph. As it draws it, you might notice that cotangent, like cosecant, is an odd function. If you were to rotate this 180 degrees about the origin, you'd get the same graph back. That's what makes it an odd function. Finally, as mentioned, cotangent's period is 180 degrees, or pi, just like tangent. That's some of the properties of reciprocal, also known as secondary trig functions.